Welcome to this presentation on deblocking filtering in VVC by me, Kenneth, my co-authors Kiran, Masuru, Dimitru, Sunshuke. Why do we need deblocking? Deblocking is used to reduce vertical and horizontal discontinuities between adjacent blocks in block-based video coding. Discontinuities can occur due to one of the following cases: difference in motion parameters used to predict the adjacent blocks, non-zero transform coefficients used to compress the prediction error of at least one of the blocks, intracoding used for at least one of the blocks. So, how to decide where to deblock? Based on checks on coding parameters in blocks adjacent to the block boundary, such as difference in motion parameters, or if one block has non-zero transform coefficients, or if one block is intracoded, a boundary strength is derived. A boundary with boundary strength 0 is not deblocked. Boundaries with non-zero boundary strength is further checked for spatial activity based on samples that can be used by deblocking. Only boundaries which have less spatial activity than thresholds are allowed to be deblocked to avoid removing natural edges. The thresholds are dependent on the quantization parameter, which controls the fidelity of the transform coefficients. So what in VVC can have an impact on blocking artifacts? Well, main impact comes from large coding blocks and large transform sizes. Coding block size up to 128 by 128, transform size up to 64 by 64 for Luma, and 32 by 32 for Chroma. Additional impacts due to flexible partitioning. We have a large range of coding block sizes from partitioning by ternary and binary splits in addition to quad-tree splits. Furthermore, sub-blocks inside coding blocks can also be generated by, for example, sub-block transforms, intra-sub partitioning, but we also have sub-block prediction from affine motion compensation and sub-block temporal motion vector prediction. So how do we take care of block artifacts from large blocks? Long tap deblocking is introduced to combat with discontinuities from large blocks, here exemplified for vertical boundary. For both Luma and Chroma, decisions whether to apply deblocking is made for a boundary segment. Spatial activity is checked for the first and last line of a segment. For Luma, modification of up to 7 Luma samples parallel and adjacent to the block boundary in block P, respectively block Q, when the width of block P is 32 or greater, respectively when the width of block Q is 32 or greater. Otherwise, only up to 3 samples are modified. The filter design is based on linear interpolation to be simple but very efficient. For Chroma modification, up to 3 Chroma samples parallel and adjacent to a transform block boundary in transform block P and transform block Q, when both have a width equal to or greater than 8. How do we take care of block artifacts due to flexible partitioning? For Luma deblocking, we need to handle deblocking of boundaries of large blocks and boundaries from sub-block prediction. We do this by deblocking sub-block prediction boundaries on an 8x8 grid, and we limit the number of Luma samples that can be modified by deblocking to enable parallel-friendly deblocking and still manage to deblock sufficiently. To manage discontinuities from relatively large blocks that can end up on a 4x4 Luma sample grid, the deblocking operate on a 4x4 Luma sample grid for coding and transform block boundaries, but the number of samples modified is limited for close boundaries to enable parallel-friendly deblocking. For Chroma deblocking, it's applied on an 8x8 Chroma sample grid, and boundaries only due to difference in motion parameters are not deblocked for Chroma. Here are examples of the number of samples modified by Luma deblocking of vertical boundaries. Boundaries with a width of 4 on at least one side of a block boundary is limited to at most modify 1 sample adjacent to the block boundary. Blocks with a width of 32 or larger on at least one side can modify 7 samples, but since the block contains sub-block prediction in this case, the number of samples to be modified is limited to 5. It is also shown that the number of samples modified for a subblock prediction boundary closest to the block boundary is limited to 2 on both sides. Otherwise, filtering with at most 3 samples on respective side of a boundary is applied. So how can the deblocking be controlled in VVC? Because usage of high dynamic range and wide color gamut is expected to increase, VVC deblocking introduced deblocking control based on luma level. This is performed by determining the luma level based on average of 4 luma samples. The QP used for deblocking is then adjusted based on the luma level. This can, for example, be used to apply stronger deblocking in bright regions. The amount of deblocking can also be controlled by parameters that control deblocking strength and how much spatial activity is allowed for deblocking to happen. This is performed by adjusting the QP used for deblocking with offsets. Individual control is also possible for all color components in VVC. So how complex is VVC deblocking? The complexity of the luma deblocking is similar to the HEVC luma deblocking. Extension of the HEVC deblocking with long tap filter design is based on linear interpolation. Only large blocks are invoked for long tap deblocking. Additional boundary strength checks due to 4x4 grid operation, but less spatial activity checks when boundaries are close. The complexity of the chroma deblocking is greater than HEVC chroma deblocking. Transform block sizes can also be deblocked in addition to intra-block boundaries. Filter decision based on spatial activity for the introduced long tap deblocking. Parallel friendly. All vertical boundaries, respectively all horizontal boundaries, can be deblocked independently. Blockwise processing for low delay application with same number of line buffers as in HEVC deblocking. So 4 lines for luma and 2 lines for chroma. Here you can see the objective performance of the blocking in VVC for different test conditions, such as intra-coding, random access coding, low delay coding. The left side shows the average bitrate increase at same PSNR and decoder time impact by disabling the deblocking filter. Y corresponds to luma, U and V corresponds to the chroma components. A positive number means increase of bitrate, and negative number means decrease of bitrate. Decoding time percentage lower than 100% means reduced decoding time. Here it can be seen that there is about 1% bitrate increase when disabling the blocking. But for all intracoding, there is a bitrate decrease of 0.6%. The objective performance benefits of VVC deblocking is less compared to the benefits seen for deblocking in HEVC. One reason is that VVC includes additional loop filters like ALF that takes part of the gain. Objective performance of VVC deblocking can be further improved by application of deblocking in RDO or tuning of deblocking control parameters. The impact of the long tap deblocking filter on objective performance is relatively minor, as can be seen on the right side there. It's also a minor impact on decoding time. But for disabling deblocking, it can be seen that the decoder time impact is significant, which typically is the case for deblocking in video coding. So here follows a visual example of how deblocking perform compared to other in-loop filters. We have an example sequence race sources and its low delay B test condition at QP37. On the top left, we have VVC without any in-loop filtering enabled. On top right, we have VVC with the blocking disabled. In bottom left, we have in-loop filtering by only enabling the blocking. In bottom right, we have VVC in-loop filtering as is, using all the in-loop filters, luma mapping with chroma scaling, deblocking, sample adaptive offsets, and adaptive loop filter. Demo is looping twice. So what was the outcome of this example? Well, if you look in the example 1, you saw PVC without any in-loop filtering, and there it was very clear that there exist block artifacts. In example 2, when the blocking was disabled, it's also very clear block artifacts, but it's a bit better than without any in-loop filtering. In example 3, when only the blocking was applied, block artifacts were removed. In example 4, when you apply all in-loop filters, block artifacts are removed, but also other coding artifacts. So, conclusions. The blocking keep to play an important role in block-based video coding and contribute significantly to the subjective performance of VVC. The main contributions in VVC deblocking can be summarized as long tap deblocking for both Luma and Chroma, flexible deblocking strength control also based on Luma level, which can be useful for HDR wide color gamut. Control mechanism to adapt filter length for various transform and prediction modes. Parallel-friendly design. In the paper you can find more details of VVC deblocking. In addition to that, here's a list of references. In the first reference, low-level details on the deblocking filter in VVC can be found, and other things related to the standard. Other references refer to other recent MPEG ITU standards. Most reference relates to contributions on deblocking during the standardization of VVC. Thank you for your attention.